Hey everyone, so today's video would be about mathematical derivation of the equilibrium condition and of the optimal quantities of the output. Till now we have seen what is a budget line is and what is a utility function. The equation of budget line looks something like this, where Px represents the price of good X and Py represents the price of good Y. M represents the income of the consumer, which is also his budget constraint because he is constrained by his income. The slope of the budget line is the ratio of prices, which is Px by Py, and it is taken in absolute values, meaning we know that the budget line is downward sloping, so its slope is actually negative. But since we want to look at the absolute terms, we want to look at it in a way that we are not considering the signs of the slope or any other value, so we will be considering the slope to be positive, or we will take in absolute terms. The utility function that we have seen till now is only the Cobb-Douglas utility function, but there are many other utility functions as well. A utility function is the equation of the indifference curve that represents the utility level of an individual consumer, meaning given an consumption bundle, if I plug in the quantities of X and Y given to me into the utility function that we have, we will get a utility level that the consumer would be deriving from the consumption bundle that was provided to us. So this was the journal form of a Cobb-Douglas utility function. This is called a Cobb-Douglas utility function, and it represents well-defined preferences. Well-defined preferences means that the consumer's preferences follow all the axioms of rationality that we have already discussed in previous videos. And like I said, that the utility function is the equation of the indifference curve. So there are two methods to get the equilibrium condition. The first one is that the slope of the budget line is equal to slope of the indifference curve, and the second one is the method of Lagrange, where we form a Lagrangian function and use differentiation to get the first order conditions, and I will be explaining it further into the video. Now there are few prerequisites that a person should know before looking into the mathematical derivation of equilibrium condition, which is you should know how to differentiate a function like we do in mathematics. You should know differentiation from mathematics and how to solve two linear equations simultaneously. So the first method to derive the equilibrium condition and the optimal quantities of the output is we have to equate the slope of the budget line to the slope of the indifference curve. Now, before delving into the mathematical derivation, if I were to give you an intuitive idea first, it's suppose that we are plotting an budget line and that we have plotted an indifference curve, and we want to get the equilibrium quantities. We know that the income of the consumer is the constraint that is set upon him, and that he cannot consume more than what his income is allowing him to consume. And he also wants to achieve the highest utility, meaning he also wants to consume such a bundle that is giving him the most satisfaction, and he has to do that within his constrained income. So wherever the indifference curve is touching the budget line, or we can put it into a mathematical way, that wherever the budget line is tangent to the indifference curve, that is where we will get the equilibrium output that we want to get. So when we equate the slope of budget line and slope of indifference curve, we know that the slope of the budget line was the price ratio, that is px by py, and the slope of the indifference curve is mrsxy, that is marginal rate of substitution. Marginal rate of substitution is actually showing how the consumer substitutes one good to consume one of another, more of another. Like he would be, if the consumer wants to consume more of good X, then he would be substituting it with, meaning he would be giving up more of good Y to consume more of good X, or conversely, if he wants to consume more of good Y, then he would be giving up more of good X. So taking the equation of the budget line from earlier and the utility function from earlier, we get something like this, that the marginal rate of substitution is actually the ratio of the marginal utilities that the consumer is getting when he consumes an additional unit of X and Y. The numerator is marginal utility of X and the denominator is marginal utility of Y. Marginal utility, as I have already said, is the additional utility or the additional satisfaction that a consumer is getting when he consumes one more unit of the good. So we actually get the marginal utilities by using partial differentiation, meaning we have to differentiate the utility function partially. Here we use partial differentiation because we assume that the other variable is a constant, and in case of total differentiation we have to use the chain rule. So using partial differentiation, the partial differentiation is represented by del, which is del u. When we want to find the marginal utility of X, it is del u by del y, and marginal utility of Y is del u by del y. Sorry, the marginal utility of good X was del u by del x, and marginal utility of Y is del u by del y. So when I partially differentiate or take partial derivative of the utility function, it is del u by del x. Substituting the utility function in place of u, we get something like this, del the utility function by del x. So doing the differentiation of this, we know that since we are differentiating with respect to X at the moment, we know the power of whatever the power of X is, it will come down and it will be reduced by 1. So alpha will come down and alpha in the power will be reduced by 1. And since we are doing the partial differentiation, y will remain a constant. So the marginal utility of X is this: alpha multiply X into the power alpha minus 1 multiply Y into the power beta. Similarly, when we'll be seeing the marginal utility derived from Y, it would be del u by del y. Substituting the utility function in place of u, we get this, and when we do the partial differentiation, we know that beta will come down and the power of y will be reduced by 1. So the marginal utility of y would be beta multiplied x raised to the power alpha multiplied y raised to the power beta minus 1. Since marginal rate of substitution was the ratio of marginal utilities of X and Y, we can also write it as del u by del x divided by del u by del y. And since we have already found the marginal utilities, we just need to substitute them into their places. Once substituted, we can make some cancellation in the numerator and denominator. We can cancel this term from here. Since this is 1 less power of x, it will be wholly cancelled, and in the denominator we will be only be left with x. Similarly for y, in the denominator the y term will wholly be cancelled, and we will only be remained with 1y in the numerator. So the value of marginal rate of substitution is alpha divided by beta multiplied y divided by x, and this value is also the slope of the indifference curve. Till now we have only found the slope of the indifference curve, and now we will be equating it with the slope of budget line to get the relation between x and y. So the value of the marginal rate of substitution that we got was this, and the slope of the budget line is the price ratio, which is px by py. Now equilibrium strikes where the slope of the budget line is equal to the slope of the indifference curve. What does this mean? It means that at this point, wherever the slope of the indifference curve is equal to the slope of the budget line, first and the foremost, that graphically we will see that the budget line is tangent to the indifference curve, and this also implies that the consumer is consuming the bundle that exhausts his entire income. Also, the consumer is consuming the bundle that provides him maximum utility. Now, why is that? Anything that is not exhausting the consumer's entire income will be giving him less utility, and anything that can give him more utility would be outside his given income, meaning it would be an unaffordable consumption bundle, so the consumer cannot consume it. The consumer can only consume whatever is his income is allowing him, and he will consume it in such a way that his utility or his satisfaction is maximized. So there is only one way that the consumer can maximize his utility, that is by consuming his entire income. So like we said, that the condition to get the equilibrium condition is to equate the slope of the indifference curve and marginal rate of substitution. Once we have equated the slope of the budget line and slope of the indifference curve, we get this expression, and by making few adjustments and manipulation, we can send the alpha beta ratio to the left hand side, and we can send the denominator, the x in the denominator, to the left hand side as well. Doing that will give us a relation between x and y, where y equals px by py multiplied beta by alpha multiplied x. This is the relation between x and y, and we can get the optimal quantities of x and y using this relation. We just have to plug in the y back into the budget line, and hence we will be getting the optimal bundles. So using the relation between x and y back into the budget lines equation, we have to substitute it in place of y, and I have written this py here. Once substituted the value of y that we get from earlier, we get something like this. Here we can cancel out the py and py term. Once cancelling out, we get the equation as px multiplied x plus beta divided by alpha into px multiplied x equals m, which is the income. From this equation we can take out px and x common. Once we do that, the inside expression is 1 plus beta divided by alpha equals m. Now taking LCM here, we get the inside term looks like alpha plus beta divided by alpha. We can send this term to the right hand side. Once sending it to the right hand side, it will get multiplied by the income, which is m, and eventually we will get the optimal quantity of x, which is, for x the optimal quantity is m divided by px multiplied alpha divided by alpha plus beta. And if we use this optimal quantity back into the equation of the budget line, or we can use this back into the relation of x and y we got from earlier, we can get the optimal quantity for y as well, which is m divided by py multiplied beta divided by alpha plus beta. Hence this is how we get the optimal x star and y star. The x star and y star are the optimal quantities that the consumer will consume when budget line touches the indifference curve. By touches, it means that the budget line is tangent to the indifference curve. X star and y star is the maximum utility bundles, meaning they give the consumer the maximum utility, and it also consumes the entire income of the consumer, meaning the consumer is spending everything that he earns on consumption of the goods. So this was all about the first method, that is the slope of the budget line is equal to slope of the indifference curve, and next we will be seeing the method of Lagrange. So the second method, that is the method of Lagrange, here we would again need the equation of our utility function, that is u equals x raised to alpha and y raised to beta. The equation of budget line is again the same, px multiplied by x plus py multiplied by y equals m. So this is how we set a Lagrangian function, where we define a function L that is comprised of the utility function and the budget constraint, meaning the equation of the budget line that we have. The Lagrangian function actually signifies that we have our utility function and we want to maximize our utility given a constraint, that is the constraint of the income. So whenever we are setting up a Lagrangian function, it shows that the consumer wants to maximize his utility that he is deriving given the constraint of the income, and here this lambda term is the multiplier. So we want to maximize utility subject to the budget line or the budget constraint. Here we will use differentiation again, and using partial differentiation again, and by using partial differentiation we will get the first order conditions, and these first order condition will lead us again to the relation of x and y that would be identical of the relation that we got from the method of slope of budget line equal to slope of the difference curve. So first we have to differentiate the Lagrangian function with respect to x. So differentiating it with respect to x, we would get del L divided by del x equals the alpha will come down, and in the power alpha will reduce by 1 multiplied by the constant that we are holding right now, which is y raised to power beta, plus here we can see that we can see from our Lagrangian function that wherever there is the x term, it will be left out, and wherever the x is not present, it will be since we are considering all other variables as constant into the partial differentiation, it will turn out to be 0. So since px was only with x, we will only be left with px, and m and py multiplied by y will become 0. This is how partial differentiation works, because we are considering all the other variables other than x right now as constants. So with the multiplier lambda, we would only be left with minus px equals 0. We have to equate it to 0 so that we can get the first order condition. So now that we have differentiated, we can send this term to the right hand side, and so once sending it to the right hand side, we know that sign changes, so this minus sign would become plus, and we don't need to write plus sign everywhere. So the first condition, the first order condition that we get is alpha multiplied x raised to power alpha minus 1 multiplied y raised to power beta equals lambda px. Similarly, when we differentiate the Lagrangian function with respect to y, it would be del L by del y. This time beta will come down because we are differentiating with respect to y, multiplied x raised to the power alpha multiplied y raised to power beta minus 1 plus lambda. This time only py will remain, because see, in the Lagrangian function, since we are differentiating with respect to y and only py is with y term right now, so we would only be left with minus py and rest will become 0. So the second first order condition that we get is beta multiplied x raised to power alpha multiplied y raised to power beta minus 1 equals lambda py. We have sent it again to the right hand side to get the condition. Now the third step is to divide the first equation by second equation. By dividing it, we know that here again we can make some cancellation. From numerator, the x will be cancelled wholly, and in the denominator we would be left with only 1x, and in denominator we can cancel out y wholly, and in the numerator we will only be left with 1y, and the expression would turn out to be something like this. This is again leading us to the same relation that we got from the first method. So once using the first order conditions that we get and dividing them, we get the same relation of x and y that we were getting earlier from the first method, and by making some manipulations we again get the same value for y, which is equal to beta divided by alpha multiplied px by py multiplied x. Now the fourth step is that we have to differentiate the Lagrangian function using the multiplier lambda. It would be del L by del lambda. The whole of the utility function will become 0 because it didn't have any lambda term, and with the equation of the budget line we actually had a lambda, so it would turn out to be 1, and we will left with m minus px into py, m minus px into x minus py into y equals 0. So by taking px x minus py y to the left hand side, we get px multiplied x plus py multiplied y equals m, which is the equation of the budget line. Now using the relation between y and x back into the budget line, we can substitute it in place of y. From here px and px will get cancelled, and from here on the procedure is similar, and we again get the optimal values or optimal quantities of x and y, which is x star m divided by px multiplied alpha divided by alpha plus beta. For y star it is m divided by py into beta divided by alpha plus beta. So these were the two methods using which we get the equilibrium condition and the optimal quantities of the output. And that was all for this video. Thank you for watching.